can start recording now. Okay. Okay. So now you make me the host again. And start. Okay. So I'm the host again. Okay.
Yes,
all right. Okay. So let's carry on then. So we've defined the horizontal lift and we've shown that it's an inverse to d pi theta restricted to the horizontal subspace h theta. So therefore we get that as a immediate corollary that d pi theta restricted to the horizontal space h theta from h theta to TPM, this is an isomorphism. So we get that the dimension of h theta is also n. Okay, so the vertical space v theta and the horizontal space h theta both have the same dimension n. And secondly, we get that h theta direct sum v theta is equal to t theta tm. And also we get that if I look at the connection map restricted to the vertical subspace v theta, this map from v theta to TPM, this is also an isomorphism. Okay. So the first part, there's nothing to prove. We just showed that d pi theta restricted to h theta is an isomorphism because it has an inverse L theta. Now for the second part, we know that the dimension of v theta and the dimension of h theta, both of these are n. So let's look at the intersection of h theta and v theta. So if xi belongs to h theta intersect v theta, then by what we proved in the previous lemma, that L theta composed with d pi theta restricted to h theta is identity of h theta, we get that xi is equal to L theta of d pi theta xi, right? This is because xi belongs to h theta. But now xi also belongs to v theta. So d pi theta of xi is 0. So this becomes L theta of 0, which is 0. So that means xi is 0. So therefore, the intersection of h theta and v theta is 0. And both have dimension n. And the sum of the dimensions is equal to the dimension of t theta tm, which is 2n. Therefore, t theta tm is h theta direct sum v theta. Is this clear? Okay. Any questions? Is this all right? Yes, anyone?
Yes.
Yes, sir, it's fine.
Okay. All right. So now we look at the connection map k theta restricted to v theta. So if xi belongs to the kernel of k theta restricted to v theta, then that means that xi belongs to kernel k theta intersect v theta, which is h theta intersect v theta, which is we've just shown is 0. So therefore xi is 0. So therefore the kernel of k theta intersect v theta, this is trivial. Therefore, since the dimension of v theta is the same as the dimension of TPM, this means that k theta restricted to v theta from v theta to TPM, this is an isomorphism. All right. So that gives us the third part of the lemma of the corollary, rather. Is this fine? Yeah.
Yes, sir.
And so finally, we also get similarly that this j theta map, which was d pi theta comma k theta from t theta tm to TPM direct sum TPM, this is an isomorphism, right? Because you look at the kernel of j theta. So if j theta of xi is 0, that means d pi theta of xi is 0 and k theta of xi is 0. That means you're in the intersection of the vertical subspace v theta and the horizontal subspace h theta, and that is 0. So therefore, the kernel of j theta is trivial, and both of these spaces have the same dimension 2n. Therefore, this map is an isomorphism. Okay. Is this clear?
Yes, sir.
Okay. So as you were saying, Orkojit, for this, we didn't use that the connection is compatible with the metric. This works for any connection on the tangent bundle. Is that clear?
Yes.
Right? You'll have a decomposition into horizontal and vertical subspaces, which have the same dimension and both are isomorphic to TPM. And this pair d pi theta k theta, this will be an isomorphism to TPM direct sum TPM. Okay, so now using this, we can now, so let's just understand a bit that if I have xi in t theta tm, and xi I write as xi horizontal plus xi vertical. Okay. So this is in h theta direct sum v theta. So here xi h belongs to h theta. It's the horizontal part. And xi v is the vertical part. Okay. So then what is j theta of xi? So this is d pi theta xi k theta xi. So this is equal to d pi theta of xi h, because d pi theta kills xi v, which is in the vertical space. And similarly, k theta kills the horizontal part xi h. So this will be k theta of xi v. And so, in other words, xi h horizontal part the horizontal component, this corresponds to d pi theta of xi, which is the same as d pi theta of xi h in TPM. And xi v, the vertical component, corresponds to k theta of xi, which is k theta of xi v in TPM. Okay, so as we drew earlier, we have the picture that we drew earlier, that here is your tangent vector PV. And we're taking some deformation of it. So this vector here is the change in the foot. This is the horizontal, this corresponds to the horizontal component. Okay. And the change in the head I get by, I parallel transport V along this curve over here, and then I look at, I mean, my tangent vector is given by derivative of a curve. I look at the, so that's a vector field along the curve gamma. I look at that here. So this change, so if this is W and this is Q, so I'm looking at QW as a change in PV, then this distance here, this is the change in the head. So this corresponds to K theta xi, and this corresponds to d pi theta xi. And so now we've got a full decomposition of the tangent space into horizontal and vertical components. So we can use this to define, now if we have a metric on M, so now we can get a metric on the tangent bundle called the Sasaki metric. Okay. And so how do we define it? So if theta is a point PV in TM, then for xi eta, which are tangent vectors to Tm at theta, so the elements of T theta Tm. So then we define the inner product. So I'll write this with a double bracket, xi eta. This is defined to be the inner product in TPM between d pi theta xi d pi theta eta plus the inner product between k theta xi k theta eta. Okay. So it's clear that this is bilinear in xi and eta, right? Because these d pi theta and k theta are linear maps. And this satisfies positivity, right? Note that if inner product xi is 0, then this implies that the inner product xi will be norm d pi theta xi squared plus norm k theta xi squared. So this is 0. So that will imply that d pi theta and k theta of xi are both 0. And we know that if these two are 0, then xi has to be 0, right? Because j theta was an isomorphism. So therefore, xi is equal to 0. Okay. So therefore, this Sasaki inner product, it is actually an inner product on T theta Tm. Is this clear?
Yes.
Okay. And using this inner product now, it's easy to see that, for example, if let's say xi is vertical and eta is horizontal, right? Then this inner product will be 0, right? Because if xi is vertical, d pi theta of xi will become 0. So the first term vanishes. And if eta is horizontal, then k theta of eta will become 0. So the second term also vanishes, right? So therefore, that means that the horizontal and vertical subspaces, they are orthogonal to each other. So note h theta is orthogonal to v theta, and h theta direct sum v theta equal to t theta tm. This implies that these must be orthogonal complements of each other, right? So this implies that h theta is equal to v theta perp and v theta is equal to h theta perp. Is this clear? Yes?
Yes.
So we've got the picture that we wanted. The horizontal and vertical become perpendicular to each other. Huh. And these d pi theta, k theta, you can think of as orthogonal projections, actually, right?
Yes.
Okay. And also note that d pi theta restricted to h theta from h theta to TPM this is an isometry. Right? Because if xi belongs to h theta, then norm xi squared, this is equal to norm d pi theta xi squared plus norm k theta xi squared and if xi is horizontal then k theta xi is 0. So this becomes just norm of d pi theta xi squared. So that means d pi theta is an isometry when restricted to the horizontal subspace, right? Okay. Yes. Is this clear?
Yes, sir.
So what does this mean? This means that this pi is actually what is called a Riemannian submersion. So this means, so I'll explain what that is. This means that pi, so we'll use this fact later, that pi from Tm with the Sasaki metric to m with its usual metric is a Riemannian submersion. So let me define that. We'll use this later. So the definition is that um, f mg1 to say ng2, a map between Riemannian manifolds, which are I'm assuming a submersion. So a submersion between Riemannian manifolds is said to be a Riemannian submersion, or just Riemannian is Riemannian so everyone knows what a submersion is, right? Between manifolds. It's a map whose derivative is surjective at each point. A smooth map whose derivative is surjective at each point. A surjective map whose derivative is surjective at each point. Okay. So is Riemannian if for all P and M, df at P restricted to the orthogonal complement of the kernel of dfp from the orthogonal complement of the kernel of dfp to TFPN is an isometry. So this is the definition, and the picture is basically you have so here is, for example, say this is say M, and F is like a projection. This is F mapping to say N. Okay. And if I take a point P here, okay, and this is f of p, and this is p. So what will the kernel of df look like? It will look vertical in this picture, right? This is the kernel of dfp. And this will be the orthogonal complement. So that will look horizontal. So this is the orthogonal complement of the kernel of dfp. And this is the tangent space TFPN. So this map from this orthogonal complement of the kernel to the tangent space below, this map is an isometry. Okay, so in this direction, you preserve lengths. In the complementary direction, you collapse lengths, right? Points map to 0 in the complementary direction. Is this clear?
Yes. It is a partial isometry.
Yeah, you can think of it like that. Yeah. Right. Yeah. Is this okay? Okay, so the projection from the tangent bundle of a Riemannian manifold with the Sasaki metric to the Riemannian manifold, this is an example of a Riemannian submersion. Okay, so we'll use this later. All right. Now what we want to do is look at the geodesic vector field on the tangent bundle. Right, so remember there was a vector field on the tangent bundle whose integral curves were the corresponded to lifts of geodesics to the tangent bundle, right? Horizontal lifts of geodesics to the tangent bundle. Right, I mean the flow of this integral of this vector field was the geodesic flow on the tangent bundle. Right, so let this be the geodesic vector field on TM. So then for any point theta in the tangent bundle, PV, right? What is the, so this is an element of the G theta is an element of T theta M. So that corresponds to an element of TPM plus TPM, right? With respect to the isomorphism J theta. So what is that going to be? With respect to that isomorphism, the horizontal and vertical components of G theta. So J theta of G theta. Any guess what this will be? Anyone? Any guess? Any idea what this will be? Yes? Well, let's do the calculation and then you'll see. Okay. So let gamma be the unique geodesic in M. Such that gamma 0 is P and gamma prime 0 is V. Okay. Then G theta, this is equal to ddt at t equal to 0 of the curve in the tangent bundle gamma t comma gamma prime t, right? Yes.
Yes.
So by definition, this will be an element of t theta tn. Okay. So let's stop here. We have less than a minute. So let's stop here and then we'll join again in the next session.